All right, here's one more example of general combined loading. This one's nice, it's a little easier to see. So we have a circular tube with an outside diameter of 40 inches, or 4 inches, sorry. I have a given and find here. Okay, I'm going to move this. Well, I'll just write it in a different color. So we have outside diameter equals 4 inches, a wall thickness T equals 0.083 inches. So to get the inside diameter for our calculations, we'll subtract that twice. And it's subjected to loads. Px, that's this one, is 1,360 pounds. Pz is 950 pounds. And the torque is a moment, so that's here, and that's 8,420 pounds times inches. All right, so then it tells us that A is 6 inches, and we're supposed to determine the normal and shear stress that exist at point H and point K. Okay, so anytime we have a torque, we're going to have a shear stress at both of those points in the same direction. So whenever we have a torque, we have the shear stress equation. Shear stress equals that torque, which is a moment. So in this case, we'll just plug in the 8,420 pound inches. We'll plug in just that to T. Times C, that's the distance from the center of, so from the center, and we want the maximum, so all the way to the outside, where we're calculating the stress all over J. So we'll calculate J. Okay, so then if we have a moment, we'll have a bending normal stress. Both Pz will create a moment around X. And that moment will change along the height of this. So, and Px will create a moment around Z. And that moment will change along the height of this. So whenever we have a moment that changes along the height, then we're going to end up with bending shear stresses too. So bending shear stresses, equation for that is the shear stress from bending equals the shear force V times Q all divided by I times the thickness. And don't forget that the thickness is 2 thicknesses because we'll be cutting through 2 and we'll need 2 thicknesses. Okay, then the bending normal stress, Px, when it bends around Z, it'll put K in compression, and Pz, when it bends around X, it'll put H in compression. So here we have sigma, the bending normal stress, equals the moment caused, so that'll be Pz times the perpendicular distance to H, so that'll be 6 inches, and Px times the perpendicular distance to K, so 6 inches. So the moment times Y, that's the distance from the neutral axis, so that's in the middle to the point where we're calculating the stress, outside, so that's the radius, all divided by moment of inertia. And we don't use our negative sign here, we just think about it. And both of these are going to be bending around here, so we'll have compression, and we'll be bending around here, so they'll both be in compression. Okay, so then I think the next thing to do is calculate section properties. So we don't have an axial force, so we won't have an axial stress, so we don't need the area. We're going to need J and I and Q. The nice thing about these circular sections is that Q will be the same when we're calculating it for K or when we're calculating it for H. It's just when we put in, the force will change. But Q will stay the same, so we can calculate all of these right away. So J equals pi over 32 times the outside diameter to the fourth minus the inside diameter to the fourth. So the first thing we should do is calculate the inside diameter, which is d minus 2 times the thickness. So we have 4 minus 2 times 0.083, and we get inside diameter. I guess I didn't calculate it here. Well, let me calculate it quick, because I think that's nicer to do than plugging it in every time. So we have 4 minus 2 times 0.83. So we get 3.834 inches. Okay. So then here, this will be pi over 32 times 4 to the fourth minus 3.834 to the fourth. And we get J equals 3.9194 inches to the fourth. Then for I, we get pi over 64, so this will be half of J, d to the fourth, minus inside diameter to the fourth. Pi over 64 times 4 to the fourth minus 3.834 to the fourth equals, we get I is 1.9597 inches to the fourth. And then Q is, for circular sections, it's either 0 or at the neutral axis, it's 1/12, for our purposes anyways, times outside diameter cubed minus inside diameter cubed, and we get 0.638 inches cubed. All right, so then we can think about what forces are going to cause shear stresses. So if we draw PX here, and then we make a cut perpendicular to that through H, we will have Q. So we will have bending shear from PX, and that's at H. And you can see that here where we have PX going this way, and so the top will have an arrow going in the positive x direction. So, and just draw that right now. Okay, then for PY, that's going to go this way. So if we drew a line perpendicular to that at H, shear stress would be 0. So, but if we draw PZ, but if we draw a line perpendicular to that through K, now we have a Q, and so we're going to have bending shear from PZ at K. And then again, we can go up here and look. This is going in the positive Z direction, which is the top face of this will go the positive Z direction. The shear stress is going to make it go this way. So I think it's nice to draw right on there whenever you can to visualize it. Okay, so now similarly we have these same cuts that we have up here with the same coordinate system. So this is cut and we're looking down on this. So Z and X are the axes we're looking at. So we have Z going to the left and positive X going down. So those are drawn on the drawing. So it's good to make sure you identify that. So then, if we draw the forces, what we're doing here is we've cut it right through H and K. So the forces, we can move those straight down, and we have that PZ is 950 pounds. And we have PX, the positive X direction is 1,360 pounds. Now we can draw all the moments that are happening here. So here we have Z and X and Y would be coming straight out. So we can draw that kind of like this. So Y is coming straight out of the longitudinal axis. So in the X direction, we're going to have a moment from the force in the Z direction. So we'll have a double arrow in the positive X direction. So we use our right hand rule to determine that. And it's going to be PZ. So 950 pounds times, so we're taking PZ times the distance to H, which is the 6 inches. So 950 pounds times 6 inches. So this moment is 5,700 pound inches. Then we're going to have a negative moment in the Z direction from when we take a moment from PX around Z. So that's going to be a negative X direction moment, or Z direction, sorry. Yeah. So we're taking PX around here. Around Z. Yeah, and then negative. Yeah, so we'll go, it'll make our thumb point in the negative Z direction. So we have this green moment is px 1,360 pounds times the distance to where we cut, which is still 6 inches, and that equals 8,160 pound inches. Okay, and lastly we have that torque. So they gave us that value. It acts in the around, it's a moment around y in the positive direction. So it's 8,420 pound inches in the positive y. Okay, so those are all of our forces and all of our moments happening at the plane of H and K. So now we just need to calculate our stresses, and we've thought about this. So we know that at point H, here, we identified that this green line here is a shear from PX. And then we are also going to have a bending normal stress from PZ. So that'll be sigma equals my over I. And then at both of these, we'll have a shear from torque. Okay, so let's analyze point H first. So from PX, we have a bending shear stress that equals the shear force, which in this case is PX, times Q all over I times T. Okay, so we have 1,360 pounds times Q, 0.6368. We calculated that at the beginning, inches cubed, all divided by I, which we calculated, 1.9597 inches to the fourth, times the thickness is 2 thicknesses, so we can calculate that either 2 times the thickness or the outside diameter, 4, minus the inside diameter, 3.834. Those are all inches. And we get 2,662 psi. And then I think it's important to draw a stress block of that. So if we're looking at H, we're looking at it, that means X is going to come out to the right and Y will be going straight up, and this green line is the shear stress we're talking about. So it'll go in the positive X direction. So if we draw our coordinate system, we have X and Y, and we have a positive shear stress on the top. And all we need to know is one face, and then we can draw the rest of the faces. Okay, now, so the next thing, we know we don't have a shear stress from PZ, because we're looking at H, and PZ will go this way. So if we cut it here, that would be 0. So no shear stress from PZ. Bending shear stress anyways. Okay. But we do know we have a bending normal stress from PZ that's going to put H in compression. So, and that would be PZ times 6, and our PZ is the 950, so that's going to be our MZ, so that's 5,700 pound-inches. Oh, sorry, our MX. Sorry, this is our MX, the red. 5,700 pound-inches, MX, not MZ. Okay, so from PZ, we get a bending normal stress equal to the moment from PZ times Y, all divided by I. So we get 5,700 pounds times inches, which is that 950 pounds times 6 inches, times Y, the radius, the distance from the neutral axis to where we're calculating the stress, so that's 2 inches, all divided by I, which is I is 1.9. I see what I'm doing. Okay. 1.9597 inches to the fourth. And we get a bending normal stress of 58.17 psi. And we've talked about how that will be in compression. Now, if we look one more time, so we're bending from PZ around X. This is in compression, and K is at the neutral axis. So K, the bending stress from PZ, is 0 at K, and it's what we just calculated at H. Okay, so no bending stress. Oh, and if we looked at the moment that PX creates, H is at the neutral axis. So no bending stress from PX, just a shear bending stress, not a normal bending stress. Okay, then we have the shear stress from the torque. Shear stress from the torque, which is caused by the moment around Y. That equals the torque times C all over J. They gave us the torque equals 8,420 pounds times inches. The radius, C, is 2 inches, and J is 3.9194 inches. So we get 4,296.5 psi. And then we draw a stress block. Has the same coordinate system, X and Y. Torque spinning around this way, making the shear stress on top of H go to the right. So these two shear stresses will add at H. And those are all the stresses at H. So now we combine, we can draw a stress block. This is H. Bending stresses and bending normal stresses act along the longitudinal axis, so those will be in the y direction. And it's in compression, so it's very important that we draw our coordinate system. So in the y direction, we have bending normal stress in compression. That is 5817 psi. And we have two shear stresses. We have the bending shear stress, which is 2662 psi. Then we have the torsional shear stress, goes in the same direction. And that one is 4296.5 psi. So we'll add those two together to get our final stress block for H is going to be, shear stresses go in the same direction. It's the last picture. And combine, that equals 6959 psi. Okay, and then the normal stress stays the same. There's only one of those. It's in compression, 5817 psi. Okay, there's one answer. Let's do K. All right, so point K, the shear stress from torque will be the same. But we'll draw a new coordinate system. So that stays the same. Okay. But we need to, coordinate system, we're looking at K. We're looking straight this way. So it's going to be Z to the left and Y up. So we have positive Z to the left and Y up. And the shear stress still goes in it'll go in the negative Z direction. Okay, so we're going to have a bending normal stress and a bending shear stress. So the bending normal stress will come from Px. It'll put K in compression. The bending shear stress will come from Pz. So that, I drew this wrong. Okay, that'll be this green arrow. So the red arrow was from torsion. The green arrow is the bending shear stress from PZ. All right, so from PZ, we have shear stress from bending equals VQ over IT. V, the shear force, is PZ, 950 pounds. Q, we calculated. It's 0.6368 inches cubed. I is 1.9597 inches to the fourth, and the thickness is the outside diameter minus the inside diameter, so we get both thicknesses, or you could do 2 times the given thickness. And we get shear stress from bending is 1,859.7 psi. And we already drew the arrow a couple of times on the picture. It's going the opposite way of the torque. It's going in the positive Z direction because the force causing it is going in the positive Z direction on the top face. Okay, so then we have a bending moment. Bending normal stress. That's going to come from PX. We'll go way back up here. This bending normal stress around Z. It's going to come from PX. So it'll be the 1360 times 6. This one, the 8160 pound-inch moment. So we have from PX, we get sigma equals my over I. That equals the 8160 pound-inch moment times the radius, 2 inches, all divided by I, 1.9597 inches to the fourth. We've looked a couple of times again and decided that that will be in compression. 8,327.7 psi in compression. So those are all the stresses on point K. So then we can put those together on the stress block. K here. Our only normal stress is in compression in the Y direction. So we have Y positive, Z positive to the left. Bending normal stresses act along the longitudinal axis, so in the Y direction. So we have compression here. And here, that's our 8327.7 psi. Then we have two shear stresses that are going in opposite directions. We have the shear stress from torque going this way. That is 4296.5. And then we have the shear stress from bending. Opposite orientation. So when we add those together, see which one bigger. This is only 1859.7. So the shear stress from torque is bigger, so we'll be going in the direction of the shear stress from torque. We'll take that shear stress from torque, 4296.5 minus 1859.7, and we'll end up with 2940 psi. And then the bending normal stays the same. There's no axial normal stress, so we don't have to add anything here. And that's our final answer.